Gravity of a larger Saturn acting in concert with Jupiter could have sucked in and destroyed all the smaller planets. Thankfully, Saturn never follows this fateful path. Instead, it grows into one of the crowning glories of our solar system.
Whenever I show people planets in my telescope, I always save Saturn for last. It's beautiful, it's so stunning. It's definitely a gorgeous planet because of its large rings.
The rings are made up of billions of fragments. These fragments continually grow and disintegrate due to the conflicting gravitational forces of Saturn and its moons. Uranus lies nearly twice as far out from the Sun as Saturn. Both it and Neptune are icy worlds, with much less gas than the other gas giants.
In a sense, they got to the feast too late.
Uranus is a plain-looking place, a flat blue-green color, thanks to a layer of methane high in its atmosphere. Since it forms further out, it becomes an ice giant rather than a gas giant. Temperatures average minus 350 degrees Fahrenheit. Since Pluto has been officially downgraded to dwarf planet status, blue Neptune is now our outermost planet. Until recently, these bodies were thought to mark the very edge of our solar system.
Our idea of the solar system changed drastically, really, in 1992 when this structure that we call the Kuiper Belt today was discovered.
Around 28 billion miles out from the Sun, the Kuiper Belt, home to an estimated 70,000 large icy objects.
There's a whole population of leftover dregs of planets formation, you can think of it as, right, where these things haven't quite come together.
Then, 1,000 times more distant from the Sun, lies the mysterious Oort cloud, comprised of up to 6 trillion comets. Most of these probably formed much closer to the Sun, as part of the same process that formed the planets. But the gravitational influence of the young Jupiter and Saturn may have forced most of these objects onto very long orbits, carrying them to the far reaches of the solar system. The outer edges of the Oort cloud are now thought to be the final frontiers, almost a full light year out from the Sun. Beyond our solar system lie billions of other stars, many with planets of their own.
For a long time, it's been one of the holy grails of astronomy to actually find a planet around another star. The only solar system, the only planets we knew about were our own. So what was that first planet going to be like around another star?
Then in 1992 comes the discovery they've been waiting for, the first ever detection of an exosolar planet. A planet orbiting a distant star.
And then the very first planet we find outside our solar system is bigger than Jupiter, way up against the star. It completely threw out everything that we'd been taught about solar systems.
There is absolutely no way that an object that big could form close to their star. There's just not enough stuff there.
The nature of these planets simply doesn't fit within standard models of solar system formation. And it's not just a problem for distant worlds. When we look back in at our own solar system, it becomes clear there are problems with the standard theory of how our planets formed.
It's interesting, when we try to apply our models, our understanding of planet formation, to Uranus and Neptune, they fail utterly. You just can't build those planets where we see them today.
There simply should not have been enough material available at this distance from the Sun for planets this size to grow. It's a mystery. Uranus and Neptune seem to be in the wrong place. And this is just one of several mysteries that standard nebular theory cannot explain. There's also the enigma of the Kuiper Belt. According to the model, it shouldn't really be there. Even more puzzling, our moon's craters all seem to date from the same time. Together, these problems threaten to undermine scientific understanding of how the solar system formed. The moon may be our closest neighbor, but it still harbors secrets. With no substantial atmosphere or weather, the lunar landscape experiences little change. So it was believed that one impact strike every few thousand years would be enough to explain its cratered surface. But then the Apollo missions brought back lunar rock samples, including crater debris thrown out by ancient impacts. And these samples tell a very different story.
It became clear as we studied the moon that a large number of the impact craters formed around 3.9 billion years ago. And clearly there was a high concentration of impacts on the moon during that time.
Lunar geologists used radiometric dating to assess the age of the samples. It came as a big surprise to find out that a high proportion of moon craters formed during one relatively brief period of bombardment. Dr. David Kring is an expert on this phase, known as the late heavy bombardment, or lunar cataclysm.
This evidence from the moon is actually telling us something about the entire origin and architecture of the solar system and how it evolved.
Tens of thousands of large meteorites must have hit the moon during the lunar cataclysm. Earth, too, must have taken a pounding. Today, only younger craters, like this 20 to 50,000-year-old example in Arizona, remain on Earth. Most older craters have disappeared, but 3.5 billion years back, there'd be no chance of missing them.
We're talking about 20 to 40,000 impact craters that would have had enough energy to change global conditions.
Where could such a vast number of impact objects come from?
Within the impact craters, we have chemical traces of the objects that produce them, and those point to the asteroid belt.
It seems to match. The objects that once hit the moon are chemically consistent with the rocks found in the asteroid belt. So this is almost certainly where they came from. But today, most asteroids are in stable orbits. There's nothing obvious that could force thousands of them out of the asteroid belt and into the inner solar system. So for decades, the bombardment was a scientific puzzle. In 2004, Hal Levison had a eureka moment. Working with an international team, he came up with a new model of solar system formation.
It's like a light going off. You sit in your office and you say, I've solved this problem people have been working on for decades, and I'm the only one in human history that understands this little part of the problem we're trying to solve.
Levison's idea assumes that the planets might have formed in very different orbits and then moved. Most scientists had believed the solar system was stable and relatively predictable, but many experts now think this is wrong.
This flies in the face of conventional wisdom. Astronomers probably always thought the planets formed where we find them today. These new numerical simulations, which show that they migrated a substantial amount and even had close encounters that caused them to switch their order, is startling and new.
In Levison's simulations, Jupiter and Saturn tugged on each other whenever their orbits came closest together, but overall these pulls canceled out. Only when Jupiter circled the Sun exactly twice for every time Saturn circled once did something dramatic seem to occur. It's called a 2-to-1 resonance, and it happened 3.9 billion years ago.
And that configuration actually makes the planets jiggle with one another. They perturb one another.
Instead of canceling out, the two planets' gravitational tugs then work in the same direction. To Levison, it's just like pushing a swing. Each well-timed push nudges the swing higher. For Jupiter and Saturn, each gravitational nudge stretched their orbits until they reached their present-day patterns. But the process had a fateful impact on other planets.
Uranus and Neptune can't stand that at all, and they just go totally bonkers. The orbits cross one another, they gravitationally get close to one another, one of them gets thrown out, the other one gets thrown in, they rattle around off the Jupiter and Saturn.
According to the theory, Uranus and Neptune may even switch places, ripping surrounding swarms of asteroids out of their orbits. It's a recipe for disaster. Some asteroids are thrown out into space, while others are pushed into the sun. Thousands slam into the inner planets and Earth's moon. It sounds like an improbably chaotic transformation, but the evidence now suggests this did happen. It could never happen today. Jupiter and Saturn are now too far apart. But this event may have been a key moment in the formation of our solar system. But the really incredible thing is that it could so easily have turned out very, very different.
You could have the wrong type of star. You could have too many giant planets. There are many ways things can go wrong. And we're right there on that thin, lucky line of existence.
Instead of the diverse solar system we now see, we could have remained forever as ashes, gas, and dust. And what of our future? 5 billion years from now, as our sun runs out of fuel, it will expand, consuming some of the inner planets. Other planets may survive as ghost worlds, still orbiting their dead sun. There will be no life of any kind. But for now, we are lucky to be alive.